Okay, so the biggest puzzle of physics. I think the biggest puzzle is that it exists at all. I don't mean the physical world, I mean that physics exists. It's a strange and interesting fact that evolution produced an animal one or two steps above the monkeys, which can not only reason and think, but be curious and follow the dots and ask the question, why is the world the way it is? But not only ask the question, but to answer it, to avoid all the pitfalls of wrong directions and eventually get to the pot of gold. Well, not the complete pot of gold, but certainly to get to the quantum mechanics, to get to gravity, to get to the standard model of elementary particles and so forth. That is an extraordinary fact. Now, of course, theory has had help. The help comes from experiment. We're entering, or perhaps I should say, maybe even 20 years ago, we entered into a set of questions where we really cannot hope that direct experiment is going to be able to guide us, at least not for many years, more like many decades, maybe even a millennium. I don't know how long it's going to take until we have experiments, or if we will ever have experiments that will help us guide us through this question of what is the connection between quantum mechanics and gravity. Do we have any tools? Well, yes, we have tools. There are thought experiments. There are paradoxes, apparent conflicts of principle, where two different principles, both of which you have reason to believe, tell you opposite conclusions. Einstein, of course, was a master at this kind of thinking. There's mathematics and logical consistency. These are the tools that we hope will be enough to carry us through, perhaps not to the very end of why the world is exactly the way it is, but at least allow us to make progress and understand more things. All right, now, my story for today, which is about quantum mechanics and gravity, begins in the year 1687, when Charlie Brown was sitting under a tree, an apple tree as it turns out, reading his favorite book. His favorite book, in case you don't know, was Dirac's, the famous Paul Dirac, who, in case you don't know, was one of the greatest physicists of the 20th century, his textbook on quantum mechanics. When, pop on his head, he was struck by a thought. His thought was, should I try to quantize gravity? A lot of people, incidentally, I'm not a very good historian. I hope I'm a better physicist than a historian. I'm telling you the history as I made it up. But as it happened, many people had already tried to quantize gravity. Dirac, Feynman, DeWitt, Weinberg, Wheeler, Hawking, all great physicists, many great physicists at one time or another had tried and didn't succeed for the most part. What do I mean by quantized gravity? Well, there were a set of rules that were put in place by Heisenberg, by Schrodinger, and eventually by Dirac himself, a set of rules for taking a classical theory. It could be the harmonic oscillator, it could be the theory of planetary orbits, otherwise known as atoms, and converting from a classical theory to a quantum theory. That was called quantization. It had a set of equations. These equations are simply the iconic equations that go into the concept of quantization. I'm not even going to read them to you. Sometimes they led to computational tools such as Feynman diagrams. That's a typical Feynman diagram in quantum electrodynamics. But when applied to gravity, they simply led to frustration. The earliest frustration is that everything you tried to compute came out infinite, but that was not the worst problem. Physicists were used to getting infinities and answers and learned to deal with them. The real problem was black holes. Black holes simply didn't want to fit into the context of quantization. Let's not worry about whether they can be made consistent with quantum mechanics. They did not want to fit into the paradigm that Dirac and other people had invented. Let's talk about black holes for a minute. Black holes are the smoothest, most well, let's just call them smooth. Incidentally, what you see when you see a black hole, when you see an image of a black hole, is you see the horizon. You don't see into the deep, dark secrets at the singularity of the black hole. Light cannot get out from those regions. Light can get out from the horizon and no deeper in. And so what you actually see is the horizon. And a black hole, a non-rotating black hole, would look so perfectly spherical, far more spherical than the shiniest ball of stainless steel or anything like that. It is perfect sphere with no structure on it at all. And physicists sometimes say that black holes have no hair. By that, they simply meant that they appear to have no structure whatever. On the other hand, another aspect of black holes is that has been thought almost since the beginning that somebody jumping into a black hole won't encounter a hard wall, but will pass right through the horizon and happily move on their way until they get too close to the singularity. So Snoopy here jumps into the black hole, perfectly happy for a while, and does not encounter any hard surface of the black hole. Let me come back to this for a minute. So things can enter the black hole, but once they have entered the black hole, according to standard wisdom, no evidence for them ever can get back out. The geometry of a black hole is such that for something to come back out, it would have to exceed the speed of light, and we all know the speed of light cannot be exceeded. So things that are thrown into a black hole or jump into a black hole are lost forever. Well, the next point of our story, the next part of our story, involves an epiphany that Charlie had. By this point, Charlie was no longer calling himself Charlie Brown, he was calling himself Jacob Bekenstein. And in 1972, Jacob Bekenstein had an epiphany. His epiphany was that black holes have entropy. Now, let me ask Matt. Matt, are I still connected?
You are still connected, yes.
Good, excellent. Every once in a while, just to keep myself from getting paranoid about getting disconnected.
No, you're there. Somebody asked whether the black hole is still perfectly spherical immediately after an object falls in.
No, immediately after it will have a bump in it where that person fell in, but that bump will disappear incredibly quickly, very quickly. For the case of a solar mass black hole, that bump would disappear in about a millisecond and becomes very spherical very quickly. All right, now, Charlie said, I think black holes must have entropy. Why would he say such a thing? Or Jacob Bekenstein. Why would he say something like that? Well, the first thing is to understand what is entropy. Entropy is by definition hidden information. What do I mean by hidden information? Why is information ever hidden? Well, sometimes it could be because you locked it in a box and threw away the key. But there are other reasons why information can be hidden, and let me give you an example. Here's my bathtub full of water, warm water. It's been allowed to come to equilibrium. It's been allowed to sit there for a month. The surface of the water is perfectly flat because it's come to equilibrium, and the water is not moving, it's not stirring, it's in equilibrium. What information does Charlie need to know in order to know whether he should get into that bathtub or not? Well, first of all, he better know there's some water in it. It'd be nice for him to know the volume of water in the bathtub. He also might like to know the mass of the water to make sure that his bathtub was not so heavy that it would crash through the ceiling. He would like to know the temperature of the water for sure, to know that he wouldn't get burned. But that's about it. There is no more information. What else could it be? The water is perfectly flat, perfectly homogeneous. It has a volume, a mass, a temperature, not much more than that. And that's all the information that is in that bathtub full of water, except that it's not. If we looked through a microscope, it would have to be an awfully good microscope, but if we looked through a microscope, we would discover that the water was made of atoms, molecules, water molecules. And there would be an incredible amount of hidden information. The position and the velocity, or the position and the momentum of every molecule. In a bathtub, there's about 10 to the 29th molecules. The entropy, or the hidden information, would be about 10 to the 29 bits of information. Why is it hidden? It's hidden for a simple reason. The molecules are simply too small to see and too numerous to keep track of. That's what entropy is, hidden information. Well, we've already established that things can fall into the black hole and disappear, become hidden in effect. And so black holes must have entropy, must have hidden information. This was basically Bekenstein's reasoning. I've oversimplified it, of course. And Bekenstein had a technique. It's a very elementary technique, which I could explain in a few minutes. I don't have time. But he estimated that the amount of entropy that a black hole could hold, the amount of hidden information, was proportional to the area of the horizon times a bunch of constants. The speed of light cubed, 4 in the denominator, Newton's gravitational constant, Planck's constant, a number. The entropy of the black hole, the missing information, not the missing information, but the hidden information, is proportional to the area of the black hole. Incidentally, this number c cubed over 4g h bar, it corresponds to an area of about 10 to the minus 66 squared centimeters. And so the entropy is the area of the black hole measured in these units of the tiny, tiny, tiny little area. Now, can we explain why area was the right thing rather than the volume of the black hole? Yes, to some extent, and here's the argument. Everybody knows who has thought about black holes that if you're watching matter fall toward the black hole, you will never see it pass through the horizon. It will slow down, there will be time dilation, the matter will Lorentz contract, it will get thinner and thinner and form a thinner and thinner sedimentary layer just above the horizon of the black hole. I said the black hole has no hair. Well, evidently it has this little bit of hair, but as that material that composed the black hole falls in, it gets squashed closer and closer to the horizon, but never passes through it. So it's there. There is information, and that information, as seen from outside, is all stored on the horizon of the black hole. So it's not completely surprising that the amount of information that the black hole can store is proportional to the area of the black hole. But then, let's just expand Snoopy out here a little bit. What about the picture that we had earlier, where when Snoopy falls into the black hole, oops, we lost him. It's hard to see him once he falls through the horizon, but he's there. That Snoopy, in fact, doesn't get stuck at the horizon of the black hole, at least in his own frame of reference. He simply falls through. There seems to be a kind of mismatch and a conflict between what happens to Snoopy when he falls into the black hole. Does he get pancaked and squashed at the edge of the horizon, or does he fall through? And frankly, it's believed that both of these are true in a funny way. We get to ask the question now, is it possible that the information in Snoopy's body, in his cells, in his brain, and all the different features of Snoopy, can that information in some sense be in two places at the same time? Squashed and pancaked against the horizon of the black hole, and at the same time in his own reference frame, freely falling into the black hole. This was a question that Hawking raised, Hawking and other people. Now let's go on a little bit. Let's ignore that question for a minute. We'll come back to it. Black holes have entropy. Entropy means heat. Heat always means radiation and evaporation. Anything that is warm will radiate energy slowly. If it radiates energy slowly, it means the energy of that black hole will have to decrease. And if the energy decreases, it means the mass of the black hole decreases. The mass of the black hole will imply that the radius of the black hole will decrease. Energy going out in the form of photons, the black hole shrinking, 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 shrinking until it disappears. When it disappears, we can ask, what happened to Snoopy who fell in? In fact, was it Snoopy? Maybe it wasn't Snoopy. Maybe it was his brother Spike. What remembers? There's a rule of physics. You can't lose track of information. What remembers what fell into the black hole after the black hole is completely evaporated? Well, one good answer is maybe the radiation that went out stores all the information that fell in a very scrambled form. In fact, that's a principle of physics. If you like, we could call it what goes in must come out. In a physicist's language, it's called unitarity, but all it means is that while information can get scrambled, it cannot get destroyed. That basic principle is there in Newton's physics, Hamilton's physics, Maxwell's physics, Einstein, Dirac himself, Feynman. Every law of physics since Newton involved this idea that what goes in must come out, which means that information cannot be lost. On the other hand, Hawking said, no, black holes are different. The horizon of a black hole is a one-way filter. What goes in stays in. Why? Because for it to come out, it would have to exceed the speed of light. This was a conflict of principle, a Gedanken experiment, a thought experiment, which led to a real conflict of principle, and I would say to confusion, to an impasse that lasted for 20 years or more, where the path seemed to get thinner and thinner and peter out altogether in a contradiction. Well, the legend is that a certain bearded physicist had an epiphany. And the epiphany occurred when he was walking in the halls of Stanford at a small science laboratory, a science museum that existed at one time in Stanford Physics Department, when he saw something called a hologram. A hologram, as you know, is a three-dimensional image which is stored on a two-dimensional surface. The two-dimensional surface is a photographic film. Think of in this picture here, the photographic film is the surrounding material on the surface, and the image is the image in the interior. It's a hologram. This is not, well, is it real? What is real? Incidentally, what is real? Is the stuff on the boundary here real, on the film, or is the stuff in the bulk here, which we normally call the bulk inside the cavity here, is it real? Well, you could say that both of them are real. In some sense, all of the information about this dinosaur has been stored on a two-dimensional film. It can be reconstructed. The reconstruction is through the use of light, but it doesn't matter what it is. What a hologram is it's a representation of three-dimensional physical objects in terms of two-dimensional surface degrees of freedom at the boundary of a region of space. That's what you can think of as a hologram. If you were actually to look at the holographic film, what you would see would look nothing whatever like this dinosaur. It would just be a bunch of scritchy, scratchy, random markings on the film, which would in no way look like what it represents. So the hologram is a two-dimensional surface whose details encode a three-dimensional system. That could be the most general definition of what we mean by a hologram. The epiphany that the bearded physicist had was that perhaps the black hole is functioning as a kind of hologram. The black hole horizon being like the film where the information is stored, and the actual reconstruction of the three-dimensional objects falling into the black hole being like the image. Why is this interesting? Well, it's an example of a sense in which information can be at two places at the same time. That information is first of all stored on the film, in this case the horizon, and it is also stored in the bulk in the interior of the black hole as a kind of image. It was a kind of existence proof that you can have three-dimensional worlds being stored as two-dimensional information, and that information in some kind of sense can be in two places at the same time. Okay, so that was the idea of a black hole. Well, let's just examine it a little more. That was the idea of a black hole as a hologram. But then what happens when the black hole evaporates? What happens when the black hole evaporates is that the film evaporates, molecule by molecule or photon by photon. The outer boundary of the system just decays and gives off photons and eventually disappears. Where is the information that fell into the system? It's in the radiation which went out, which carried away the information that was on the surface. What happened to the image on the interior? Well, there's just no hologram left. It just disappears, it's gone. But that's not a violation of the idea that, that information is conserved. Where did it go? It went back out into the surrounding environment. That was the idea of a black hole as a hologram. A little bit later, through the work of Gerard 't Hooft and other people, and Juan Maldacena, myself a little bit, it was understood that not only a black hole, but the whole world or region of space of the whole world could be understood as a hologram. The idea was that if a region of space has a maximum entropy, a maximum amount of hidden information, and a black hole is the maximum amount of information that can be stored in a region of space, then it must be that you can describe that region of space by a system a quantum system whose numbers of degrees of freedom is proportional to the area of the region. A region of space can be described by a quantum system on the boundary with an area's worth of degrees of freedom. That was the idea of the holographic principle. Whole worlds, if we surround them by a mathematical surface, can be represented by a quantum theory, which is like the holographic film, whereas the region that they're describing is like the image of the hologram. We have these two sides to things: a quantum description, which is stored on the hologram, and a gravitational system. Or by gravitational system, I mean systems which contain gravity, maybe also quantum mechanics, and are what we all ordinarily think of as the reality, that they are represented as a kind of image of a hologram. This idea, which was a nutty idea at first, it wasn't taken seriously by too many people, eventually, largely through the work of Juan Maldacena, became a main staple of current physics. It is not only widely accepted, it's the basis for almost everything that's taking place in the area of the connection between quantum mechanics and gravity. All right, that's the holographic idea. Now I want to turn to the idea of entanglement. We're going to be very quick about entanglement. Entanglement was something, I don't know exactly who discovered it first, but it's usually attributed to, of course, as all good things, to Einstein, Podolsky, and Rosen. E, P, and R, keep those letters in mind. They stand for entanglement. In 1935, long after his heyday, Einstein, together with Podolsky and Rosen, introduced, or at least expounded on the idea of entanglement. So what is entanglement? I'll try to explain it very quickly. Let's suppose that, is this Bob? Let's see, it says on his shirt. No, it's Joe Cool. Well, I'm going to call him Bob. And this lady over here who looks a lot like Lucy, I'm going to call Alice. Alice and Bob each have a piece of quantum information, what a physicist would call a qubit. It could just be the spin of a particle, the spin of an electron. And that spin can point in any direction. You can measure the spin, its components in various directions. And if Alice and Bob's qubits have never been in contact with each other and are completely independent, then Alice can know a great deal about her qubit, and Bob can know a great deal about his qubit. They can make predictions about what they'll measure, and they know a good deal about their own qubits. But there are also states, quantum states, which are called entangled, where the situation is entirely different. In fact, the quantum state, the knowledge of the quantum state, would tell Alice or Bob nothing whatever about their own qubits. In fact, it would have no information at all if each one of them did an experiment on their qubits. But yet, they know as much as can be known about the pair of qubits. How can that be? How can you know everything that can be known about a system and not know anything about its parts? What do you know if you don't know about the parts of the system? And the answer is correlation. What Alice and Bob will know if they have a completely entangled state of a pair of qubits is they will know correlation. For example, Alice will know that if she measures her qubit along the component of her qubit along the z-axis, the component of her spin along the z-axis, and she gets plus, or if she gets up, she discovers her qubit is in the up direction, then she instantly knows that Bob's qubit is down. That's correlation. If she measures her qubit along the x-axis and she gets it pointing along the x-axis, she knows that Bob's qubit will point along the minus x-axis. Likewise along the y-axis. So this is correlation, although each one of them knows nothing about what they will measure. If they measure their own qubits, they do know what the other one will measure once they measure their qubits. It's called correlation. It's not causation. It's not a violation of any principle of physics. It's just correlation. Two particles which are entangled in this way are usually called either an EPR pair for Einstein, Podolsky, and Rosen, or a Bell pair for the great theorist John Bell, who I won't tell you what he did, but he turned this idea of entanglement into a very quantitative idea. So two particles which are entangled, usual to draw a line, or sometimes one draws a line between them just to indicate the entanglement. You can sort of think about it as some connection between them, but it does not mean that somebody who passed between them would encounter something. In fact, they would not. That's the idea of entanglement. And entanglement is a useful thing to have, an entangled pair. You can do things with it. I'll give you an example. I realize that I'm jumping all over the place. We're going to tie things up, but let's do the jumping for the moment. Quantum teleportation. Quantum teleportation is something that you can do if you have a pair of entangled qubits. The entangled qubits are the pink ones here. The pink one here and the pink one here are entangled. And Bob and Alice share them. Bob has one half, Alice has the other half. But Alice also has another qubit. That's a qubit which is prepared in some state. Alice may know what state it's in, but she's not going to measure it. What she wants to do is she wants to send that qubit, or at least the information, the quantum information in that qubit, she wants to send it to Bob. Well, there's an easy way to do it. She can just send the qubit from Alice to Bob. But she wants to do it in such a way that an eavesdropper would not be able to intercept under any circumstances. There is a trick, and the trick makes use of entanglement. I'm going to tell you what it is. I'm not going to explain it. Alice will take the two qubits in her possession, the one that's half of the entangled pair, plus the one she wants to send, and she'll combine them together and make a measurement on them, a quantum measurement. She will then send the result of that measurement to Bob in the form of a couple of bits of information. What she sends to Bob will be totally useless to the eavesdropper. It will contain no information at all about the original state of the qubit that Alice was sending. She'll send that information to Bob, and when Bob gets it, whatever the outcome, whatever he receives, it will tell him what to do next. What he does next is to apply some operation to his qubit, and if they all do it right, and it all succeeds and works out, Bob will suddenly discover that his qubit is instantly turned, or not instantly, but is turned into exactly the qubit that Alice wished to send to him. In other words, the quantum information in Bob's qubit over here will suddenly be the same as what Alice was sending him. Now, when I say suddenly, this cannot happen terribly suddenly, because it is essential for Alice to send these two little bits of information, which themselves have no information in them at all about what Alice is sending, but she has to send them as a kind of code book to Bob to tell him what to do next. This is called quantum teleportation. And it is a trick for sending quantum information using entanglement. That's the bottom line. Sending quantum information in a way that cannot be intercepted. All right, I'm finished with entanglement for the moment. We're going to jump to yet another subject. This subject is the subject of Einstein-Rosen bridges. Einstein and Rosen are the same Einstein and Rosen of EPR, but Podolsky was absent from this one. And the year, exactly the same year as the discovery of entanglement, 1935, when Einstein and his colleague discovered a new solution to Einstein's equations for geometry, for the geometry of a space-time. This geometry is today something we call, it was called an Einstein-Rosen bridge. Today it's sometimes called a wormhole. It's a connection, a shortcut in space between two very, very distant or even disconnected spaces. In this picture here, this picture is a little bit deceptive. It looks as though this wormhole connecting the lower part and the upper part here is somehow embedded in ordinary space, where if we found one, we could look at it and see the wormhole. No, that's not the way it is. The way it is, that is real space, is the surface here. There's nothing out here, forget that. The real space is the surface. There are two either very distant regions of space or completely disconnected space with a space connecting them, a wormhole, a shortcut between what would otherwise be a very long path to get from here to here. That was the solution of Einstein's equations. Now, what does it have to do with entanglement? If you would have asked me before the year 2013, or asked anybody, including, I suspect, Einstein and Rosen and Podolsky, they would have said the two have nothing to do with each other. Entanglement and Einstein-Rosen bridges. If you would ask after 2013, the answer that any plugged-in physicist who was following these things would say is that it has everything to do with the connection between quantum mechanics and gravity. In fact, it is now believed that in some sense they are the same thing. Entanglement between two things and the existence of Einstein-Rosen bridges may be essentially the same thing. This is called ER equals EPR. Einstein-Rosen, the bridges, are the same as Einstein-Podolsky-Rosen entanglement. I'm not going to try to keep track of historically who were responsible for these ideas. I'll write a book one day explaining who did what. Okay, let's flesh this out a little further. This rectangle here is just space, a very, very big region of space, so big that to go from here to here would be 1 billion light years, a very, very large distance. And at one end of the space over here, we have a cloud of particles, a dust cloud. Another end, we have another dust cloud. What do these dust clouds have never been in contact with each other. They're too far away. They've never had any interaction. Matt, are we still together?
Yes, we're still
Good.
together.
Okay. What happens to a dust cloud which is left in isolation? Well, gravity will pull it together. If the dust cloud is big enough, gravity will pull it together. It might make a star out of it. The star will burn out, and eventually gravity will pull it together and make black holes. Oh, I meant to explain what this picture is over here. This picture over here is exactly the same as this picture over here, except I've sort of folded the sheet of paper over, just so I could put one cloud nearby on the drawing to another cloud. But they're not really close to each other. To go from here to here, you have to go around the bend. So they're far from each other. I've just drawn it this way so I could get it all on a single sheet of paper. Folding the paper doesn't change anything to it. It doesn't change its intrinsic geometry. So we have two dust clouds, far, far from each other. What happens to dust clouds? They contract and eventually form black holes. I've represented the two black holes by two little dimples in space. Two little dimples in space represent two black holes which have formed from the collapse of these dust clouds. They're very far from each other. They have nothing to do with each other, and they're totally disconnected. We get a very different story if those particles, the two dust clouds, were composed out of entangled particles. If the particles of one cloud were entangled with the particles of another cloud, then we get a different story. How would we get such entanglement? Well, to get such entanglement, we would start with a bunch of particles over here, halfway in between. We would entangle them and create two dust clouds entangled, and then transport one of them over to here and one of them over to here. This is hard, but easier than it sounds. We would have two entangled dust clouds where the particles of one dust cloud would be entangled with the other. And now let gravity do its work. Again, it will make two black holes, but because those black holes are now entangled, they will have an Einstein-Rosen bridge connecting them. That's the idea of ER equals EPR, that entangled systems are connected geometrically through something very similar to the Einstein-Rosen bridge. This is a connection between gravity and quantum mechanics. On the one side, we have quantum mechanics and entanglement, EPR. On the other side, we have geometry, the geometry of a wormhole. Those are equal, maybe a strong symbol, closely related. Okay, so now let's talk about what we now have. Franklin and Linus, I believe that's his name, Franklin. Franklin and Linus are far away from each other at the opposite ends of the observable universe, but they happen to have a pair of entangled black holes. How those black holes were formed, how they got entangled, let's not ask that, but Franklin and Linus have them in their possession. Can they use them, for example, to come together? We don't want them to have to wait 10 billion light years to go from one place to another. We want to ask, can Linus jump into the wormhole? That means jumping into his black hole. Can Franklin jump into his black hole? And can they meet in the center, not after 10 billion years, but after 30 seconds or 3 seconds or 2 seconds? Can they meet in the center? The answer, remarkably, at least insofar as we have understood these things, is yes. We believe they can. So this would be a very valuable resource if Franklin and Linus wanted to jump into the black and wanted to meet and shake hands. Of course, it would be very dangerous because once they're in there, they are very quickly going to wind up being crushed together by this, being crushed by the singularity. But never mind, they can at least jump into their black holes and meet at the center and shake hands. What can't they do? What is impossible, at least according to our current understanding, is for Linus, who started at this end, to jump in and make it all the way to the other side and meet Linus outside the wormhole on his side. That would violate the principle that nothing can exceed the speed of light. There's no way to go, let's go back to this picture here. There's no way to go around the outside from here to here in less time than it takes light to travel between here and here. And in fact, there is no way to go through the wormhole from one side to the other in less time. That's a principle of physics. It's called Einstein causality. So what prevents then Linus from passing through the wormhole and meeting Franklin? Well, I want you to imagine now a tunnel. It could be the Lincoln Tunnel, it could be the Holland Tunnel, a tunnel connecting New York and New Jersey. It could, I suppose it could also be the George Washington Bridge, but I'll make it a tunnel so that it's somewhat hidden. If that tunnel exists and we want to drive through it, no problem, we drive through it. But unknown to us is the fact that this tunnel, in its hidden dimension, this tunnel is not a tunnel. It's a very special kind of magical tunnel where the tunnel actually exists in an extra dimension of space. And that tunnel has the property that it expands, it grows, it lengthens with time, just in such a way that if you drove into one end, the tunnel would expand so fast that your automobile, no matter how fast you drove, would not be able to make it to the other side, would not be able to make it through the tunnel and out the other side. In fact, even light would not be able to get through this hypothetical tunnel, which is expanding very fast. The light ray would get stuck and eventually just not be able to get any further because the tunnel is expanding too fast. That's the way Einstein-Rosen bridges are expected to behave. They expand and grow so fast that nothing can actually get through them. That does not prevent somebody from jumping in at one end and the other end from meeting in the center. That fast, it's not expanding. Wormholes, because of this, are said to be non-traversable. You cannot traverse them, you cannot go through them. Okay, wormholes grow, and that's on the geometry side. That's on the general relativity side of things. Einstein's equations tell you that these wormholes grow too fast to be traversable. What is going on in the quantum mechanical side? On the side describing the holographic description of all of this, the quantum mechanics of it. What is going on? What is it that's growing? What grows in the quantum holographic side that represents the same growth as the growth of the wormhole? So I will tell you, it's a quantity called complexity. Matt mentioned that I was involved in developments having to do with computational complexity, and I'm going to tell you now what they have to do with wormholes. First of all, what is complexity? Matt, are we still good?
We sure are.
Okay, good. I hope I'm not running out of time because I'd love to get through this, but we'll see.
You have about 12 minutes roughly.
I think we can make it. Okay, I'll illustrate the idea of complexity by thinking about a chess game. I'm not a chess player. I'm the worst chess player. I gave up chess when I started getting beaten by 3-year-old children. And this is probably a meaningless game right here. But nevertheless, you come and you see the chessboard. I think all the pieces are on the right. I don't think I have two black bishops on the same color. I think it's okay. I think it's a legal position. But you come and you see this chessboard and you ask, how did it get to be this way? What was the game that actually brought it to this configuration? Or better yet, what's the shortest possible game with the least number of moves that could have brought the chessboard to this configuration starting with the canonical starting point for a chess game. What are the minimal number of allowed moves that could have gotten us to this configuration? That is called the complexity of the configuration, the minimal number of steps that could have gotten you to this. So it's not a question of how did the chess players actually get here. It's a question of what is the shortest possible game that could have gotten here. That would be called the complexity of the position, the complexity of the chessboard at that instant. It's a computer science question, and complexity is a computer science concept. That's classical complexity. There's a notion of quantum complexity, which is very similar. It doesn't involve chessboards, it involves quantum computers. It involves the running of quantum computers. On the left side, we have some initial configuration of a bunch of qubits. Time evolves. The red lines are called gates. And what are they? They are essentially the same thing as individual chess moves. They have some properties. They're quantum mechanical, but they are chess moves. And as we go from left to right, the game is played. The game is played one step after another. Quantum gates replace chess moves, and eventually you get to a very entangled, complicated state. From an initial state was simple, you get to something complicated. The complexity is a measure of the minimal number of steps that it would have taken, the minimal number of gates that it would take to produce a particular quantum state. But you can say it another way. You can say, given the final output here, what is the shortest way that you could run backward to get to the simple state? You can either think of it as how hard is it to go from the simple, how many steps does it take to go from a simple state to a complicated state, or how many steps does it take if you wanted to work backward from complicated to simple. That's a measure of complexity. And much like entropy, quantum complexity tends to grow. If you start a chessboard in a simple position and you wait a little bit, you expect it to get more complicated, more random, more complex. So complexity, like entropy, is something which tends to grow, but for a vastly longer time than entropy grows. Let's come back to black holes and Einstein-Rosen bridges. Einstein-Rosen bridges grow with time. In fact, according to classical general relativity, they grow forever. Well, let's skip this slide. It's not too important. Yeah, yes it is. Wormholes grow forever. Complexity is something which tends to grow. And in fact, for a large enough quantum circuit, a large enough quantum computer, it will grow for a very, very long time. How long does it take a system to come to thermal equilibrium? That means how long does it take for its entropy to grow to the maximal value? Well, not very long. In particular, if the system happened to be a solar mass black hole, it would take about a millisecond for it to come to thermal equilibrium. How long, thinking of that system as a quantum system, would it take for its complexity to become maximal? The answer is an incredibly large time, e to the 10 to the 78, some incredibly long time. The point is that complexity can continue to grow long, long after the system has come to thermal equilibrium. So what do we know? We know that wormholes grow, and according to classical physics, they grow forever. We know that the complexity of a quantum system grows, if not forever, for an incredibly long time. And the basic hypothesis, which is now being tested, it's still under test. There's not a thing which is infinitely secure, is that the quantum version of wormhole growth is complexity growth. Okay, let's come back to something now. What about quantum teleportation? Isn't that a form of traversability? The whole point of wormholes growing which is related to complexity growth, is if the wormhole grows fast enough, it cannot be traversed. And that was an important concept because it prevents you from exceeding the speed of light. But what about quantum teleportation? Wasn't that a trick that allowed information to go from one point to another through an entangled system? And if wormholes are nothing but entanglement, doesn't that mean that quantum teleportation can occur through the wormhole? Could it be that quantum teleportation creates traversable wormholes? And the answer is yes. The answer is yes, but at a cost. Remember, I told you that to do quantum teleportation, information in the form of a kind of code book has to be transferred back and forth between the two sides. That information contains no information about what's going through the wormhole or what's going through the quantum teleportation, but it is necessary in order to carry out the protocol. The implication is that you can't do quantum teleportation faster than the time that it would take a signal to go from one side to the other, to go the long way around. We're almost finished. So let us suppose then that this kind of information can be transported, can be exchanged back and forth between Franklin and Linus. Given that, can Franklin pass through the wormhole and shake Linus's hand? Can wormholes be traversable? And the answer we now know is yes, that the pattern of traversability of wormholes is exactly the same as the pattern of traversability of entangled particles. In fact, not only can Linus or Franklin pass through the wormhole and come and shake Linus's hand, he can also report what he may have seen inside the wormhole, an extra photon or two. And so this back and forth, wormholes can be traversable, but not in a way that violates causality, not in a way that allows you to send information faster than the speed of light. That's the bottom line. But the real bottom line, well, I had a little bit more, but I think it's a little bit too late for this. The real bottom line, oh, I like that picture, but the hell with the picture. The real bottom line is that there is these parallel sets of ideas, one coming from quantum mechanics, one coming from gravity. They seem to parallel each other. They seem to do the same things, and in such a way that one almost has the feeling that gravity and quantum mechanics are almost the same thing, that they are much more deeply related than we ever had any reason to expect. So let's come back to Charlie now. Charlie is sitting and thinking, should he try to quantize gravity? Should he try to use the usual rules of going from a classical system to a quantum mechanical system? And I would say no. I would say no. What we found is not that quantum mechanics and gravity can't fit together. It's they are so closely related that they can't be taken apart. You cannot take them apart. They are just too closely related. Taking them apart and then putting them back together through this process of quantization is the wrong idea. Instead, we should be thinking about how, through the holographic lens, through the holographic connection, quantum mechanics and gravity are almost, or if not exactly, the same thing. Now, I've simplified many things, and I've left out many, many developments that are going on, developments which go under the words quantum error correction, page curve, replica wormholes, islands, the Python's lunch, the SYK system. All kinds of developments are happening as we sit here speaking. There are people who are developing these ideas and going ahead with them. They all have the same flavor. They have the same flavor. On one side, something quantum mechanical. On the other side, something geometric, something that Einstein would have understood as the geometry of general relativity. And there are more and more of these things are coming together in a way that, as I said, supports this idea that quantum mechanics and gravity are very, very closely related, too closely related to be taken apart. Nevertheless, we don't have a comprehensive picture of the whole thing. That still remains to be done. To finish, I just want to mention that all of the things I've talked about have been contributed to by an enormous number of, well, not enormous, a large number of younger and older physicists. None of this is solely my own work or solely the work of any single person. I started to make a list of all the people that I could think of that have contributed heavily to this, and I sort of ran out of steam. My hands started to get tired from writing. I've made a list here of some of the most important names in this subject. I'm sure I've left some out. Many of these people are very young people, just entering the subject now. They've already contributed important work, and I expect that will continue to go on. How far we will get, how far these ape-like creatures who are one generation away from the monkeys, how far they will get to answering all the questions, I don't know. I doubt that I will be here to see it, but it has been enormously exciting, enormous fun interacting with these people and pushing the frontiers ahead. Good. Thank you very much.